We left off on Wednesday talking about things like this. If I'm given a dimension on that of, let's go 1.75 inches plus or minus 0.05 inches. We talked about how that was an allowance. An allowance means that we are allowed that much on either side of our measurement, and it's still acceptable. Can anybody tell me, can you remember, what's the difference between an allowance and a tolerance? Very closely related. The allowance is the deviation here, the plus or minus. The tolerance is the size of the range, the whole range. In most cases, the tolerance is just double the allowance. So it's plus or minus 0.05. It would be, the tolerance would be 0.10 inches. Let me show you where that comes from. Remember how to get our range, our implied range, or what we call the acceptable range, works just like with our measurements where we had that plus or minus, that possible error. We took our measurement here, the 1.75 inches. We would subtract that allowance of 0.05. Gave us a bottom end of 1.70 inches. To get the upper end, we take our measurement of 1.75 plus the 0.05. So we get 1.80 inches on the top end. So we get that range. And you can see here the tolerance is just the difference between the upper end and the lower end. So we get that 1/10 of an inch tolerance. So the next step in this conversation is to talk, we talked about errors, absolute errors and relative errors. Well, we have absolute tolerances, or absolute allowances like we have here, and relative tolerances. So we had 1.75 inches plus or minus 0.05 inches. That is absolute. No matter how big this measurement is, that desired value, remember we called that, no matter how big that is, our allowance is plus or minus 0.05 of an inch, period. We can convert that into a relative allowance. By doing that, all we're going to do is find a percent. I can't spell today for some reason. Okay, so to find that percent, it's just blank over 100 equals our allowance of 0.05 over our desired value of 1.75. So we can cross multiply and divide here. 100 times 0.05 divided by 1.75. We get 2.86 basically. So that is 2.86%, because 2.86 out of 100. So this would be listed as 1.75 inches, plus or minus 2.86%. Why would we want to do that? Well, for example, let's say we're making cabinet doors. And we have several of them that are different sizes. So let's say that this one is 30.5 inches. This one is 32.5 inches. And we have one that's 24.25 inches. Depending on the situation, it may be appropriate to have absolute allowances there where each of them has 0.05 or even 1/10 of an inch or whatever, where we're allowing it to be off. Or, in some cases, the bigger it is, as we talked about with our relative errors in our measurements, sometimes if it's larger, it can be off by a little bit more. So rather than doing plus or minus a certain number of hundredths or tenths of an inch, we might do plus or minus 1%. So all of them would have the same relative error. Now that would result in a little bit different absolute error for each of them. So from that 1% relative error, if we wanted to construct the absolute error or absolute allowance, we would find 1% of the 30.5 inches. If we cross multiply and divide, 1 times 30.5 divided by 100, it's 0.305 inches. Looking at that, plus or minus 0.3 inches. That's over 1/4 of an inch. Is that probably an acceptable tolerance? Mostly not for cabinetry, no. In framing, it might be borderline even. Let's take a look at another one here. So 1% seems like a relatively small tolerance or allowance, but it's not. It's a little big for cabinetry. So let's go back to say we have that 30.5 inch door. And what would you think would be an acceptable absolute error? 1/8 of an inch would probably be still too much. Probably go down to a 1/16 of an inch. So let's go 0.0625 would be a 1/16. So let's go 0.06. Just under a 1/16 of an inch. What would that be as a relative error? So again, it's our absolute allowance, 0.06 over our desired value, and we cross multiply and divide. We get 0.196, 0.197 actually. So that's basically 0.2%. So that's less than 1/4% error that gives us allowable of that 1/16 of an inch, or under a 1/16 of an inch. Okay, so enough of dealing with the actual tolerances. You guys have any questions on the tolerances themselves, the plus or minus allowances and all that? Percents, absolute? Okay. One of the reasons we use those, or one of the things we got to be careful of when we use those, I should say, is two pieces interacting with each other. If I have two pieces, we're going to put them side by side for now. Let's say these two pieces have to fit together. Let's even put a third one on the end. So we might be looking at door panels that are butted up against each other or anything else that's fitted together. Let's say this one here is 3.25 inches plus or minus 0.05 inches. This one here, we're going to go 5.50 inches plus or minus 0.05. And this last one will go 2.75 plus or minus 0.05. There's something we call a tolerance buildup or an error buildup. And what happens is, if all the tolerances or all the allowances end up on the same end of the range, we can have problems. Now, chances are, probabilities say that it's most likely going to happen if two of those are on the high end, at least the third one's most likely going to be on the low end. Chances are you're going to have one on the high end, one on the low end, and the other one somewhere in between. There's a low probability of getting all of them on the very high end or all of them on the very low end, but it can still happen. So let's take a look, first of all, to get what the desired value here is. The desired value is just going to be the 3.25 plus 5.5 plus 2.75. Of course, those are all inches. I should have them labeled. If that adds up, we're going to get 11.5 inches is our desired value. In a perfect world, all of those would be dead on, and the total size would be 11.5 inches. If we construct the range for each of these, subtracting the 5/100ths there, this would be from 3.20 to 3.30 inches. Does that make sense? You guys see where that comes from? I'm subtracting the 0.05 from the 3.25, then adding the 0.05 to the 3.25. So what's the range for this one going to be here? 5 point what? 45, good. To 5.55, very good. 55, did you say? I say it sometimes too, don't worry. Then this one here, 2.75 minus the 0.05 is 2.70 to 2.80. So if we look at that on the low end, if it just happens that all three of those end up on the low end, we could end up with 3.20 plus 5.45 plus 2.70, which could end up giving us 11.35 inches. Or they could all end up on the high end, which would give us 3.30 plus 5.55 plus 2.80, which adds up to 11.65 inches. So looking at this, you can see here, this is a full 15 hundredths, or more than an eighth of an inch away from our desired value. That's something like, what is that, 5/32 of an inch off of our desired value. Not 5/32. That's probably unacceptable for dealing with any sort of precision work. Now that's just three pieces piled up. If you have a cabinet system sitting there where you're going to have probably a dozen or more pieces fit together to make that whole system, if they all end up on the lower end or the upper end, there's an issue there. Now, like I said, chances are some are going to be on the upper end, some are on the lower end, and they cancel each other out. But you do have to be aware of that tolerance buildup. Now, for you guys, I realize you guys are just doing the rough framing right now. You're not going to get into cabinetry this year? Okay. This does come into the woods quite a bit. If you go into like the machining side of things, CNC, which is one of the programs this class does apply to, this is huge. You get into mechanical design, dealing with metals and stuff like that. You deal with a lot of tolerances, and actually they get into a whole field of study called geometric dimensioning and tolerancing that deals with it. One of the things you consider, we talked about two parts together where the tolerances build up to either cause a much smaller piece than we wanted or a much larger total than we wanted. Sometimes we have two parts that have to interact with each other. One of these might be like my artwork leaves a lot to be desired. So you guys might have to use your imagination a little bit here. I'm not sure how I want to draw this. Pretend that looks like the deadbolt sliding in and out of the side of a door. That bolt should fit inside that hole perfectly. So I'm going to draw it like this. Here's the hole in the door, and here's that bolt sliding in and out. In an ideal world, it would fit perfectly and slide in and out. Problem is, if it's the exact same size, it's not going to move, is it? So we have what's called a clearance fit. So let's say we decide we need 5/100ths of an inch clearance for that to slide in and out smoothly without binding up too easily. Well, let's say that we size that hole at 0.80 inches. And we size then the bolt at 0.75 inches. Is that going to work? Well, again, in an ideal world, that would. In an ideal world, we'd be able to make that hole exactly 0.80 and that bolt exactly 0.75. Problem is, as we manufacture those things, there's going to be allowances, tolerances on those dimensions. So if this is plus or minus 0.03 inches in its manufacturing, and this here is plus or minus 0.03 inches. That means our hole has a possible range. What is 0.80 minus 0.03? What's 80 minus 3? 77. So 0.77. Up to the 0.80 plus 0.03? 0.83. So that hole has a possible range of 0.77 to 0.83. Still giving some clearance off that 0.75. But the 0.75 has a range as well. What's the minimum size of that bolt? Well, 0.75 minus 0.03? 0.72. Up to what's the maximum size? 0.78. So now you can see a possible problem here. The smallest size of the hole is smaller than the largest size of the bolt. So if you happen to end up with the hole being manufactured on the small end and the bolt on the large end, they're not going to interact well. Well, they're not going to interact at all. It's going to be useless. So let's take a look at how the math works on that clearance fit. So two things happen when we do that to make this work. One, we make that hole just a little bit larger to allow a bit for those allowances and tolerances. So we might instead make this 0.83 inches is what we're going to specify it to be manufactured at. Let's say that's plus or minus 0.03. The second thing we might do is tighten down those allowances. So instead of plus or minus 0.05, which is a common one, we've tightened it down to plus or minus 0.03. There. Next, that bolt that's going to be sliding in and out, we might make that a little smaller to make sure we've got plenty of allowance there. So instead of 0.75, we might make it 0.72 inches, plus or minus 0.03. So now if we look at this situation, let's look at the hole. So minimum and maximum size. What is the minimum size of that hole going to be? 0.8. Maximum size? 0.86. Good. Of course, those are inches. For the bolt, what is the minimum size of that hole going to be? 0.69. And the maximum? 0.75. So now we want to talk about clearance. So minimum clearance and maximum clearance. Our minimum clearance occurs when the hole is small and the bolt is large. And we can see there the difference between that 0.80 and the 0.75 does give us that 0.05 inches. And we had said that's the minimum clearance we need so that that'll go in and out. You need to be allowed for any sort of dirt or grime that might build up on it. They do usually put a little bit of lubrication. Oil does make things move easier, but it also does take up space. So if it's too tight of a fit, oil will actually bind it up. So we do get our minimum clearance that we need for that to work. But on the other end, our maximum clearance is when the hole is large and the bolt is small. What's the difference between those? Careful. 86 minus 69 is 17.17 inches. So we have 0.17 of an inch. That is close to 3/8 of an inch. That obviously is way too much, isn't it? Not 3/8, sorry, 3/16. Little hamster just doesn't want to stay on the wheel today. Sorry. It's a Friday. So you can see here, even though 0.03 of an inch seems like a pretty tight tolerance, it can cause a lot of issues with two parts interacting with each other. Now the other side of it is something called an interference fit. In an interference fit, we have something that is pressed in and forced to stay in. This might be if you're using a dowel to hold two pieces together. At one point, yes sir. They used to actually use wooden pegs a lot to hold, even for larger construction together, they would use wooden pegs. It still happens a lot in some of your finer furniture. They'll use wooden dowels or wooden pegs to hold things together to avoid metal fasteners. So let's say that we have a wooden dowel that's going to be forced into a hole, and what's going to hold it in there is the fact that the hole is slightly smaller than the peg itself. So you force it in there and it cannot come back out without extreme force. That's called interference. So in this case, let's say the hole is 0.24 inches and the dowel is 0.25 inches. What that means is we have the difference between them is 1/100 of an inch of interference. The peg, the dowel, is bigger than the hole. That's holding it in place. But again, this is not an ideal world. Both of those are going to have some sort of an allowance, a tolerance to their size. So let's redraw the picture. So let's say this hole, again, to allow for that allowance, we're going to make the hole a little bit smaller yet. So we might make the hole 0.22 inches plus or minus 0.02 inches. And the dowel that we're going to force into it, we might make that a little bit larger just to ensure. Make that 0.26 inches plus or minus 0.02 inches. So we look at this case now. We're going to look at the hole and I will call it the pin. And again, we're going to look at minimum and maximum size. What is the minimum size of that hole here? 0.20, good. What's the maximum size of the hole? 0.24. For the pin, what is the minimum size? 0.24. And the maximum size? 0.28. So if I'm looking at the interference, the minimum interference comes when the hole is large and the pin is small. We can see there we've got 0 inches. They're exactly the same size. So will that dowel stay in the hole? Probably will, right? Any sort of dust or grime on it's going to hold it in place. Any sort of imperfection in the surface. You guys have worked with wood enough now to know that you can never get the surface of wood perfectly smooth. So if they're exactly the same size, once you force it in there, it's most likely going to stay. What's one of the problems with wood, though, over time? What's that? Warping is one. And shrinkage is what causes warping. Yes, the shrinkage of the grain. The rate of shrinkage, if it's depending on what shrinks faster, can cause the dowel to shrink faster than the material around it. Any sort of shrinkage in that dowel can cause it to come loose. On the other side, wood is kind of funny. When the grain shrinks, depending on how the grain is oriented, let's say I have a piece of wood here with a hole in it. It is possible for, have you guys talked about shrinkage in wood at all yet? Okay. We'll go into science mode for just a second. If the grains of the wood are oriented like the blue lines there, wood tends to shrink perpendicular to the grain. So in other words, if the grain's running that way, it's actually going to shrink this way. So it could cause the edges of this to pull in some. Now the thing is those fibers, what happens is the blue lines are going to get closer together in every direction. Sometimes if you have like the heartwood of the tree near the center of that, it can actually shrink to the sides where it actually pulls the sides of the holes out like that. So you can actually get, even though the wood is shrinking, the hole in the wood can actually get slightly larger. So shrinkage of the wood can actually cause the hole to get bigger as well. So even though those are exactly the same size, and at first when we put that dowel in the hole, it's going to stick and feel tight, over time it could cause problems. Now the other side of that, maximum clearance is when the hole is at its, maximum interference I should say, is when the hole is at its smallest and our pin is at its largest. That gives us an interference of 0.08 inches, which is a little bit more than a 1/16 of an inch. Might be a little difficult to force it in. So the moral of the story is an allowance that looks small, 0.02 of an inch seems like a pretty small allowance. It's fine if you have a piece standing on its own, but when they're interacting with other pieces, it can cause a lot of problems. Any questions? Okay. So we've talked about measurement. We've talked about how pieces fit together. We've talked about how the numbers, way to express measurements, can imply the errors in the measurements and all that stuff. That's the basics behind measurement. And just so you guys know, we're not going to stress that a lot moving forward. We're not going to dwell on the whole significant digits. We're not going to dwell on the degree of precision. In fact, we're going to do a quiz today where we're going to do it as a group and get it out of the way, because it's something I want you guys to know and I want you guys to experience, but I also don't want it to be something that holds you back. So I'm going to actually pause the recording here and I'm going to hand out the quiz. Let's do an example of one similar to number 13 up here on the board. So if I have something like, let's say I've got something like 6,432 divided by 0.64. If I divide those, what do I get? We get 10,050. Now we have, when we're multiplying or dividing, we deal with the accuracy or the number of significant digits. This one has 1, 2, 3, 4 significant digits. This one has 2. So that means we have to round our answer off to 2 significant digits. So we start at the beginning, 1, 2. So we have to round it off there. Now we can't just drop those other digits, because this does still have to be 10,000. So we're rounding off there. This 0 says that's going to stay a 0. Problem is I can't just write 10,000 because this 10,000 has how many significant digits? The only significant digit is the 1, right? But we just said our answer has to have 2 significant digits. So how do I make that have 2 significant digits? I have to indicate the first 0. So as you guys look at 13, how are you going to make that show that it has 2 significant digits? Measurement. Let's talk about where measurement came from. The origins of measurement actually come from communication. You guys have experienced it out in the shop already, that when you go to do something, you need to be able to tell each other how long something needs to be. If you're right next to each other, you can say, well, it's got to be this long, and you can hold it up and mark it off. But if you're across the room or down the hall, or maybe you're just recording it so next year's group can build it the exact same size. You have to have some way of reporting that size. So measurement came from that need to communicate and record. Now I could take maybe the size of this paper here, And I could, if I wanted to measure it so that you could replicate it, I could say, well, I'm going to take my pen and I'm going to go 1, 2. My paper is about 2.5 pens long. So then you go and you take your pen and you go, okay, well, I'm going to make it 2.5. 1, 2. Well, 2.5 is way out here for you. So your piece of paper ends up being much larger. What went wrong there? Yeah, your pen was bigger than the one I was using. So for measurement to work, we have to use something that, first of all, you have to have a pen. If you don't have that object, it's not going to work at all. So first of all, we have to use something that we know the other person is going to have. Second, what the other person uses has to be really close to the same length as what we use. So these two pens would not make a good measuring device. So where measurement started, length measurement especially started, they used something that they knew that pretty much everybody was going to have, and it was really close to the same size from one person to another. If we talk about length measurement in the standard units, an inch is one of our shortest units of length. Does anybody know where the inch came from? The inch is on your thumb, from the end of your thumb to the point of that first knuckle. Now, you got to remember, this measurement started a couple thousand years ago. The average height of a man was not much over 5 feet tall, like 5'2", 5'3". So their thumbs were a little smaller. I'm guessing if most of you measured your thumb there, it'd probably be like 1 1/8 to 1 1/4 inches. Usually longer than an inch. But back then, people were smaller. So that's where the inch came from. So if I wanted to measure this piece of paper, I would take my thumb and I'd go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I got 10 inches. Now, we all know a paper is 11 inches. But like I said, our thumbs are a little bit bigger now as people have evolved to become larger. One of the sources of inaccuracy there you saw is every time I moved my thumb, I had to bring it to where the joint was, the point of my knuckle was where the end of the thumb was before. I had to move it so that it stayed in the same spot. Now, if I didn't line that up perfectly, I introduced a little bit of an error into that measurement. So that was one of the weaknesses of using body parts for measurement. I mean, you could try to stack your thumbs together, but even then, you're going to have that little bit of error. In the 500s, King Edward, and you don't need to remember his name, King Edward was kind of egotistical. He declared that his thumb and all his other body parts that they used for measurement were going to be the official measurements of the land. And even though this was kind of an ego trip on King Edward's part, it had huge strides for measurement. First big thing is now they had to come in and cut little blocks of wood to match his thumb and whatever for an inch. So now when I go to measure something, I don't have to just take my thumb and move it. I have these little blocks of wood. So I could actually take 2 blocks of wood. If I'm measuring this, I can take 1 block of wood, set it down there, take my other little block, 1-inch block, put it next to it. And I can just flip-flop them. I take this one and move it over, take this one and move it over. So as I butt these up against each other, if I'm holding them in place, I'm moving them along, and the next one is starting exactly where the one before it ended. So I don't have that error of having to move it and try to visualize where the last one ended. So that cut back. And eventually they decided, well, if I'm just going to keep moving these, why don't I take a stick and mark on that stick where those blocks ended? And that was the beginnings of our first ruler. They marked it out. Later they numbered it. And as we discussed before with our degrees of precision, they started cutting them in half to make smaller units so we can distinguish between things. What's the next unit that we use that's bigger than an inch? A foot. A foot contains how many inches? 12 inches. A foot is literally the distance from the end of your longest toe to the back of your heel. Now again, if most of you measured your foot, it's probably 12 1/4, 12 1/2 inches. Not exactly 12 inches. King Edward's foot was actually considerably shorter than 12 inches. But, in fact, there wasn't 12 of his thumbs in his foot either. But a couple hundred years after he passed on, people decided, you know what, if you measure something in feet and I measure something in inches, it would be nice to be able to tell which one's bigger. And at that time, they couldn't do that because there was no relationship between feet and inches. They were totally separate units. So they adjusted the length of the inch and the foot to make it so that there were 12 inches in a foot. So now if you measure something in feet and I measure it in inches, we can convert them so that we can compare those two numbers. Now the other thing that King Edward's move did, by declaring that his foot was going to be the official foot of the land, it made it so we didn't need some of our other units anymore. What do I mean by that? Well, if I wanted to measure the height of this wall, what units would we normally use? Feet, right. Well, if I'm going to measure this with my foot, I can get to about here with some serious stretching. Am I going to get to the ceiling measuring that with my foot? No way. The foot was only good for measuring things along the ground because that's where your feet are. If I wanted to measure the height of something like that, my foot didn't work really well. So they had other units. They used hands. A hand was the width of your hand at the base of the fingers here. That's a hand. That's about 4 inches. In fact, they adjusted it to be 4 inches. So measuring things that were vertical like that, you would use your hand because you could get your hands to go up and down easily, much easier than your feet. In fact, for livestock, horses, cows, sheep, they still use hands to measure their height. We don't need to use hands for walls anymore because now we don't have to actually use our foot. We have a ruler that can measure that foot for us. So King Edward's move of declaring his foot being the official foot of the land actually made it so we didn't need some of those intermediate units anymore. Now, bigger than a foot, we have, what's our next unit?
Yard.
The yard. And how many yards are, or how many feet are in a yard? 3 feet. Good. Anybody know where the yard comes from? A lot of people think the yard is the length of your stride, and that is approximately a yard, but the yard actually comes from the distance from your outstretched hand to either the center of your chest or the point of your nose. It was actually a tailor's unit. They'd take fabric and they pull it out, that's 1 yard. Take it again, that's 2 yards. And again, King Edward declared his yard was the official yard of everybody. And again, that was adjusted years later to make it so 3 feet fit in a yard. There were other units in between there that we don't use anymore. A cubit. You ever hear of a cubit? Cubit was the distance from the tip of your longest finger to the point of your elbow. Now, again, we're taller than we used to be. A cubit, if you measured that on me, it's about 18 inches. But back then, for most people, that was about 16 inches. Now, in the shop, do you guys have anything that's about 16 inches? A lot of things are 16 inches. Well, like, well, levels, yeah, but I'm talking about when you build stuff, you're going to do stud spacings are 16 inches. Floor joist spacings are 16 inches. Traditional rafters were 16 inches. Now with trusses, they're 24 inches usually. But most everything in construction was a cubit apart. So they would take their hand to frame a floor. They would just put their arm in there, and that's where they put the next floor joist. For framing walls, they just put their arm in there. That's where they put the next stud. So that was a very quick and handy measurement. If they had to use their foot to do that, 1 foot would be too close together, 2 feet was getting to be too far apart, while 1.5 feet was kind of tricky to do. That cubit was right there. It was really handy to use your arm for it. Again, now a standardized measurement with King Edward making his declaration. We don't need the cubit anymore. There is one unit that's bigger than a yard that we're going to use, and that is a rod. Anybody know how many yards in a rod? I've never had anybody know this one, so don't feel bad.
It's probably 5.5
5.5 yards. Easy to get when it's on the board. How many feet are in a rod? 16.5. 3 times 5.5, right? The rod was a shepherd's tool. You had a rod and a staff. The staff was the little hook, kind of like Little Bo Peep had. That was for hooking the animals around the neck, detaining them. The rod was a defensive weapon. So they measured out, it came from pasturing. Okay. We talked about this one before? Rod? No. Let's say that I have some sheep, and let's say Bryce has some sheep. Put them down in the valley, and at the end of the day, I say, well, I had 12 sheep. Bryce says, well, I had 15 sheep, and there's 20 sheep down in the valley. One or both of us is lying, right? It's going to turn into a fight.
I said you.
What's that?
I said you.
It doesn't matter.
Well, I believe.
Well, chances are probably both of us are exaggerating how many sheep we had. With cattle and horses, they solved this by branding. You could very quickly look at the animal and see whose brand was on it and know whose it was. This didn't work so well with sheep for a couple of reasons. One, their skin is a little delicate. It didn't hold the brand well. It actually damaged the skin too much, and it went into the muscle. Two, their wool grows out too thick, so you wouldn't even be able to see the brand anyway. And three, and not insignificant, wool is highly flammable. Think about that one for a second. Yeah. And at that time, ear tags and stuff like that were not readily available, so there was no way to mark the sheep to distinguish them. So they had to divide up the land. So Bryce and I would get together and we'd pick a landmark. Maybe we'd find a big rock or a tree or whatever. And we'd say, okay, I'm going to pasture my sheep over here. You can keep your sheep over there. And, well, to make it fair, we got to make sure they're the same size. So I'm going to take my rod and lay it down on the ground. There's one. Bryce would lay his down. There's two. I'd bring mine and flip it over. Three. We measure, okay, so it's 40 rods by 100 rods, and yours is 40 rods by 100 rods. We have the same size land. To this day, land is still surveyed in rods. If you look at the official survey of land, it'll say the northeast corner is 16.5 rods from this landmark, and north of this landmark, and east of this one, and so forth. So we will still use rods a little bit in this class. Bigger than a rod, and actually between a yard and a rod, there's like a fathom that we don't use anymore. A fathom was for navigation for boats. 1 fathom is about 6 feet. And it was the shallowest water that most of your large vessels could navigate through. So they literally took one of their taller sailors and threw them overboard. And if they touched ground and their head was still out of the water was too shallow to navigate through. So they didn't throw them overboard and let them sink. They actually had them walk out in front of the boat. And if they were able to swim out in front of the boat, hopefully. If they were able to sink down and put their feet on bottom and their head still came through the surface, it was most likely too shallow to navigate. Bigger than a rod, there was a furlong, which is 1/8 of a mile. The furlong was literally the distance that a horse could run at full speed without getting winded. The average horse, I'm not talking about thoroughbreds. An average horse. The next one that we use is going to be a mile. Anybody remember how many feet are in a mile?
500 or 5,640.
Careful. 5,280 feet. You're confusing for how many yards? This is where we were getting the 7.6. Yards is 1,760. That's where you're crossing them up. You're blurring the two of them together there. A mile, there's a lot of rumors out there where a mile came from. One of the rumors was it was the distance that King Edward could see out the window from his throne. I don't buy that one so much. The one that makes the most sense to me comes from the Greek and Roman military. Mil is the Greek prefix for 1,000. So if you're looking at like your property taxes and stuff, the mil rate is your price per 1,000. If you have a 22 mil rate, if you have land that's worth $1,000, you're going to pay $22 in taxes. So a mile was the distance that Roman soldiers would march in formation 1,000 paces. Now a pace was from starting on your left foot, going to your right foot, and back to your left foot. So think about that. That's about a little over 5 feet. So 1,000 paces would be 5,280 feet. Converting between these. This is going to be important for you guys, of course, feet and inches especially. If I have 4 feet, most of you can just tell me that is how many inches? 48. If we didn't know that one, we do feet to inches enough on our own that we really don't need to to focus on it, to do too much with it. But if we didn't know that off the top of our head, the way we could do that conversion actually goes back to our work with fractions. When I had 3/4, I could multiply the top and bottom of that both by 5, right? What I was multiplying by was 5 over 5, which is what? 1. I got 15/20. 15/20, even though it looks different, has the exact same value as 3/4 because we multiplied by 1. That's what we call the unity fraction. It has a value of 1. It changes the appearance, but not the value of something. So over here, we're going to use a unity fraction as well, but it's going to look a little different. Now we're getting rid of feet. So what I'm going to do is I'm going to put feet on the bottom of this unity fraction. And I'm changing it from feet into inches. So I'm going to put inches on top. The reason I did that is so that my feet will cross cancel in my fractions. What's my relationship between feet and inches? Well, 1 foot is 12 inches. So down here I put 1 with my feet, 12 with my inches. Now when we look at this, that doesn't look like it equals 1, but if you look closer, it does. 12 inches and 1 foot have exactly the same value. So when we multiply, as we said, the feet cross cancel out. 4 times 12 inches is 48 inches. On bottom, it's 1 times 1 is 1. So 48 over 1, or just 48 inches. Now, as we said, for that one, you don't need to have a conversion factor.
Is the meter not important?
Well, we're going to get to the meter. Yeah, we're going to get to that one. For that one, you don't necessarily need to have a conversion factor. But what if I give you something like 99 feet, and I ask you to go into rods? How many of you know off the top of your head how to convert feet into rods? Not so much, right? Well, let's set this up. 99 feet over 1. In our conversion factor here, our unity fraction, it's usually easiest for me to figure out what has to go on bottom. What units has to go on bottom here? We're getting rid of feet. So feet goes down. 16.5. Nice try. On top is going to be our rods, and 1 rod is 16.5 feet. So here the feet cancel out. You know what this is telling us? We have 99 times 1 rod is 99 rods. On bottom, we've got 1 times 16.5. So this will be 99 divided by 16.5, which is exactly 6 rods. Okay, you asked about the meter. The lovely meter. Metric length. Now, one of the problems with standard length is it was not standard. You know, we mentioned King Edward declaring that his thumb and his foot and his hand and his arm were going to be the official inch, foot, yard, and everything of the land. Well, he was not the only ruler that did that. In different parts of the world, different rulers that made that same declaration. So standard measurement was anything but standard. From one part of the world to another, the inch was a different length. The foot was a different length. In fact, for the English standard, there's 12 inches in a foot. In other areas, it wasn't even 12 inches in a foot. They were different. Some were 10, some were 14. It was different. So standard measurement was not standard from one country to another. So the question was, when we started to trade internationally between countries, which country's inch do we use? Which country's foot do we use? Well, it's easy to say, well, we're going to use ours because we're the biggest country or whatever, but it was a huge political issue. So that's why they came up with the metric system. This was actually back in the 1880s they developed the metric system. Most people think of the metric system as being relatively new. It is. I mean, that's what, 130 years old? But it's been around for a lot longer than most people think. Most people would say it came out of the 1970s or 80s. Anyway, when they developed the metric system, for length, their main unit of length, their only unit of length actually, is a meter. A meter, unfortunately, is a yard. Our English yard is 36 inches. A meter is like 39.37 inches. It's bigger than our yard. It would have been really convenient if the meter was equal to a yard. Well, they thought about that. And in fact, a meter is equal to a yard in the country that they developed the metric system. The metric system was developed in Switzerland, so the meter is equivalent to a Swiss yard. It doesn't help us much, but anyway, the meter is slightly longer. It's about 3.37 inches longer than our yard. So you guys know a yard, 3 feet, so a meter is about that tall. If they wanted to measure something smaller than a meter, they used prefixes to divide the meter up into smaller pieces. The prefix deci meant 1/10. So a meter was abbreviated with an M, a decimeter was abbreviated DM. That was 1/10 of a meter. The prefix centi meant 1/100th. So cm was a centimeter, or 100th of a meter. Of course, if it's 100th of a meter, that means there's 100 of them in 1 meter. The prefix milli meant 1/1000th. So mm is a millimeter, or 1,000th of a meter. Now you can see they went every 10 there, a tenths, hundredths, thousandths. They didn't do 10,000ths, 100,000ths. From thousandths, they skipped to millions. The prefix for millionths is called a micrometer. Now, mm was already used for millimeter. So what they used was actually the Greek letter for m, which is mu. It looks like kind of like a U with a tail on it, or a P that doesn't quite close on top. That's the Greek letter mu. So mu m was a micrometer. Now, in the medical field, they use micrometers and stuff for doing medical measurements. Actually, use micrograms and microliters and even more. In the medical field, it was one of the first fields that had to key everything into a computer. There is no mu key on your computer keyboard. So they actually use the abbreviation MCM for micrometer. So that can actually mean micrometer as well. Your textbook always uses mu-m, by the way. There's other units smaller. There's a nanometer. Nano is a billionth. So you think about that. A millimeter, I mean, you can barely even see the separation between my fingers. That's a millimeter. A micrometer is that chopped into 1,000 pieces. A nanometer is that chopped into 1,000,000 pieces. A nanometer is really small. You used to hear a lot about nanotechnology and nanoscience. All nanotechnology is things that are really small. An atom is about a nanometer in size. So nanotechnology is talking about building things from individual atoms. So going larger, we have deca. The prefix deca means 10. Now dm is decimeter, so for deca they had to use dam. Then they had hecto. Hecto stands for 100. So hm is a hectometer, or 100 meters. They had kilo, which is 1,000. So a kilometer is km, or 1,000 meters. Now, the same on this end. They had gone 10, 100,000. They didn't go 10,000, 100,000. They skipped up to 1,000,000. Mega was the prefix for million. Now, notice I used a capital M there, because a megameter is a capital M followed by a little m. Now, some of you may be looking at these and thinking, I've never heard of hecto, deca, maybe not even deci, because they don't get used hardly at all. For most of our metric measurement, even though they have these other units, the only ones that get used really are the main unit, milli, which is 1,000th, and kilo, which is 1,000. Now in the US, for length measurement, a centimeter gets used a lot. The only reason for that is in the US, the centimeter is the closest thing we have to an inch. And the inch is so ingrained in our measurement that we've latched onto the centimeter. But in most other countries, they actually use a millimeter more than they use centimeters. to make conversions in the metric system, if I have, let's see here, 7.2 centimeters, and I want to convert it into millimeters. Each position here, if I move one spot to the right or left on the chart, I'm just multiplying or dividing by 10. When I multiply or divide by 10, what does it do to the decimal point of the number? Yeah, it moves it left or right, one spot, right? So each spot on this chart is just a decimal place. So if I'm going from centimeters to millimeters, I'm going from centimeters to millimeters. That's one spot to the right on my chart. Conveniently, the decimal point just moves one spot to the right in the number. That becomes 72 millimeters. If I have 480 centimeters and I want to convert it into meters, on the chart from centimeters to meters is 2 spots to the left. My decimal point has to go 2 spots to the left. If there's no decimal point in the numbers at the end, of course. It goes 1, 2, that's 4.8 meters. If I have 270 meters and I want to convert it into kilometers, to get from meters to kilometers, I'm going 1, 2, 3 spots to the left on the chart. So my decimal point has to go 1, 2, 3 spots to the left. That is 0.27 kilometers. Make sense? Okay. We will talk more next week about conversions with lengths. And I'll give you the homework next week. For now, I'm going to give you a little bit of homework on the tolerances and allowances, absolute and relative. This is in the big book. It's going to be page 229, exercise 7-10, 1 through 11, the odds. And page 232 through 236. Actually, just unit exercises. So you're going to be problems 9 through 15, the odd. And problems 33 to 65, the odd. So I'll give you guys the last 6 or 7 minutes here to get started on those.